SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to this NPTEL course on Circular Economy for Sustainable Buildings. We have seen how we should conserve resources such as water and energy through various contraptions. Let us in a very consolidated manner of probably 2 lectures see how we can reduce embodied carbon in the built environment. How can we save materials, or how can we ensure that by using the materials, building materials, we do not harm the environment much. So, what are those strategies? Let us quickly see them. So, today's class will be on a comprehensive approach to reduce embodied carbon in the built environment. So, what is embodied carbon? Embodied carbon means it is the total greenhouse gas emissions that is associated with the building materials and the construction process throughout the entire life cycle of a building. So, embodied carbon means it includes all the carbon emissions which is involved in extraction of the building material, such as mining of the building material or harvesting of the raw material. Then it also includes transportation, the movement of this materials to the manufacturing site, and also the movement of the manufactured material from the factory to the site. It includes the energy required for production of building materials. For example, cement or steel or plastic, they require certain processes to be manufactured from raw material. So, that energy which is required for manufacturing plus the energy required for construction. So, the emission released during actually building the building, or assembly of the building or erection of the structure. And then it also includes end of life, which means once the building becomes obsolete or old and you want to demolish it, what is the energy required for demolishing it? All this put together is embodied carbon. But then we see that there are these phases. A1, A2, A3 is the phase which is for product phase, which is raw material supply and transport to the factory and the manufacture. That comprises of what we call as A1 to A3, and almost 65 to 85% of the total embodied carbon emission happens in this phase, where you go to the mine and then you extract, say, iron ore or bauxite, and then transport the whole thing to the factory. That itself will give about 65 to 85% of the total carbon emission of that particular product. Then we have the construction phase, which is called as A4 and A5, and that is transport to the site and installation of that particular building material on the site during the construction phase. This constitutes about 6 to 10% of the total embodied carbon emissions. And then we have what is called as use and maintenance phase. So this is called as upfront carbon. Without doing anything to the building itself, the building has been responsible for emission of so much of carbon by virtue of the choice of building material that a designer does. And then we have the B1, the use and maintenance phase is divided into three parts. One is the actual use and maintenance. Second is repair, refurbishment, retrofit, etc. And the third is the operational energy and the water used. So, this constitutes about 8 to 15% of total embodied carbon emissions. And then we have end of phase, which is once the building is used, then if you want to demolish the building, then about 3 to 15% of the total embodied carbon emissions is consumed in this phase. This is called as end of life phase, and it involves construction and demolition, and it involves deconstruction and demolition, and also transportation of the waste building material which is demolished from the site to the either the processing plant or landfill or whatever you may call it, and this is called as C1, C2, C3 and C4. The whole thing put together, which is A1 to A3, which is the product phase, manufacture of product, then B1 to B7, which is the use of the building, maintenance of the building and things like that, and C1 to C4, which is end of life. All these three phases put together is called as whole life cycle. So, the carbon dioxide emissions, which is responsible for extraction of the building material, transportation of the building material from the extraction site to the factory, and also the product which is made in the factory, transporting that to the site, the process of manufacturing, the emissions involved in the manufacture of that product, the carbon emissions which are released during construction or assembly of the building, and the end of life, which is emission from demolition and waste disposal or even recycling, all put together is called as whole life cycle. Then the embodied energy is the calculation of all the energy that is used in the manufacture of that particular product. We have what is called as recurring embodied energy. So, what is recurring embodied energy? Recurring embodied energy means it is the energy which is needed to maintain or refurbish that building over a period of time. For example, if a tap gets damaged or it is leaky, you have the choice to completely replace the tap or replace only that particular part which is causing the leak. Based on your choice, the recurring embodied energy can be high or low. For example, if you replace a very normal tap with a high-end tap in order to curb a leak, your recurring embodied energy is going to be very high. Whereas, if you just change the washer or whichever part of the tap is responsible for the leak, then your recurring embodied energy can be much less. And then we have these three definitions which you should know. First is cradle to gate. So, what is cradle to gate? Cradle to gate means it's the embodied energy of individual building components. Second is cradle to site. This is the energy required to produce the finished product. And then we have cradle to grave, which is the energy consumed by the entire life cycle of the building. And as I had already told you, the product stage comprises of A1, A2, A3, which is the emissions during the raw material extraction, during transportation and during manufacture. And then you have the emissions during construction phase, which includes manufacturing goods being transported to the site, and then the installation of that particular material on site. Then we have the use stage, which is primarily the maintenance, repair, refurbishment, replacement and also use. And then we also have what is called as operational energy use, which is not part of the embodied carbon. So, until here is embodied carbon, and during the use of the building, say in the form of use of electric current or pumping of water and things like that, which is called as operational energy. And then we have embodied energy during the end of life stage, when you are actually demolishing the building, then using some transport which also has a component of carbon emissions and dumping it onto the site. And if you are processing that waste, then that also consumes some kind of energy, resulting in carbon emissions and then ultimately disposal. Okay, so this is all the various stages. Now, I had been going on telling you about carbon emissions, carbon emission. What is this emission? What do you mean by emission? And what does that have to do with the global warming? So, we will see what is this greenhouse gas. Now, various sources contribute to the entry of carbon dioxide into the atmosphere, including the burning of fossil fuels or solid waste and chemical reactions like cement production. Also, synthetic and potent greenhouse gases like hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride and nitrogen trifluoride, they are released from various applications which have a very high global warming potential nature, and they also have the characteristic of trapping heat. Methane emissions arises from coal, natural gas, oil production, transport, also from livestock, cow and things like that, agriculture, and also organic waste being filled into lands or causing landfills. Then, for example, if you look at nitrous oxide is emitted primarily from the agricultural, industrial and combustion activity, which also contributes to greenhouse gas levels. This multifaceted array of sources highlights the complexity of addressing and understanding the different contributors to climate change. Then what is global warming potential? Global warming potential is nothing but it is a term which allows us to compare the gases by measuring the amount of energy 1 ton of a gas absorbing over a 100-year period as compared to 1 ton of carbon dioxide. So, the global warming potential is actually something we use as a term which is comparative, and that comparison is with a carbon dioxide, its global warming potential. So what does it mean? A higher global warming potential will indicate that there is more intense warming effect as compared to carbon dioxide. So this is a standardized metric and it helps us to evaluate the various contributions of greenhouse gases to this phenomena called as global warming. Embodied carbon is actually the sum of greenhouse gas emission which is released during extraction of a raw material or the ore, transportation of the ore to the manufacturing plant, the process of manufacturing, transport of manufactured goods to the site, the actual construction process, the maintenance and no the retrofit or renovation of the building, and end of life of the product system. So, embodied carbon is reported as global warming potential and it is measured with the comparison of one molecule of carbon dioxide over 100-year time frame. What does that mean? 1 kilogram of carbon dioxide has the global warming potential of 1 kilogram carbon dioxide equivalent. 1 kg CO2 is equivalent, and this 1 kilogram of carbon dioxide equivalent is converted to other global warming potential of gases. For example, 1 kilogram of methane, if you see 1 kilogram of methane is approximately 21 kilogram carbon dioxide equivalent. So, it is about 21 kg carbon dioxide equivalent. So, CO2 is carbon dioxide equivalent. So, actually carbon dioxide serves as a reference gas and is assigned a global warming potential of how much? 1, irrespective of the time frame that it is used due to its role for benchmarking purpose. The prolonged residence of these gases in the climate system can last for thousands of years and can have a very long impact. So, here in this chart, I have shown the global warming potential of various gases. For example, hydrofluorocarbons have global warming potential of range from 150 to 11,700 carbon dioxide equivalent, whereas perfluorocarbons, they have a GWP of 6,500 to 9,200, whereas sulfur hexafluoride has a global warming potential which is so high, 23,900 is its figure. Now, all these will be slightly plus or minus here and there based on the standard with which these are measured. Now, why should we address embodied carbon? What is its significance? So, here you can see that we need to consider upfront emission, which I had told you is that the embodied carbon is very unique because the emission can occur upfront during the construction process, primarily due to extraction, production and transportation of materials, which means even before the building starts to operate, you have pumped in so much of energy or carbon dioxide into that building. Unlike operational carbon emissions, which can be reduced over a period of time by improving energy efficiency, embodied carbon remains fixed. Once you build a building, that much of energy you have already trapped into that building. And then what is the role of the building industry? So, the building industry is a major contributor of global greenhouse gas emission, with a large portion coming from embodied carbon in construction materials. For example, cement and steel production, they contribute maximum to global emissions of all the building materials. Also, why is embodied energy or embodied carbon so important? Because it has irreversible impact. That is, once you build a building, once the construction process is over, you have locked in the embodied carbon. And this means it cannot be mitigated unless you do substantial retrofitting or material replacement in such a way that you take a large part of the material used in a particular building and use it somewhere else, and at the same time you replace that material which you have removed with a very low carbon material. All that no designer is going to do, because he is consciously deciding what building material he needs to use when he starts designing a building. Therefore, it is important for every designer, civil engineer, architect to address embodied carbon and ensure that his building uses very less embodied carbon. Then, now we will look at the strategies to reduce embodied carbon in buildings. The first and very important strategy is to reuse or retrofit existing buildings. What do we mean by that? It means that the existing built environment is a huge asset to achieving substantial or almost near term carbon reduction. So, we need to leverage buildings which we already have, and this can help us avoid embodied carbon emissions from new construction. Also, we should look at upgrading and electrifying existing pool of buildings without demolition, because that can reduce not only embodied energy but can reduce operational emission also. So, that accounts for 27% to 30% of the total global emissions. Now, there is also a critical time component for reusing what we already have. Now, for buildings built between say today to 2050, more than half of their carbon emissions will be from embodied carbon. So, it is estimated that if we can reuse and retrofit existing buildings, we can save anywhere between 50% to 75% of the embodied carbon that would be emitted by constructing similar kind of new buildings, especially when the embodied carbon that would be emitted by constructing similar new buildings will be very carbon intensive, because we will start looking at new structure, new envelope. But if we can reuse the existing building, then that will be very relevant in today's world, where we are trying very hard to reduce embodied carbon emission. For example, if you look at the historic district of Decatur in Georgia, this was founded in the year 1887. So, if you look at this case study, it was founded in 1887. So, when this campus became obsolete according to them, they could have demolished all the buildings and rebuilt everything. But they chose to reuse, repurpose and rehabilitate the buildings. They found that such an approach could save 34,000 metric tons of carbon dioxide equivalent. They found that it would mean that even if the entire campus was made into a forest or afforested, it would take 400 years to sequester that much of carbon. So, if nothing is done to an existing building, do nothing to an existing building, what is going to happen? And if we retrofit an existing building, so when you do nothing to an existing building, you add 0% of embodied carbon. The blue color is embodied carbon. Whereas if you retrofit, you add a small amount, which is say 351 tons CO2 equivalent, or this is 0 CO2 equivalent when you don't demolish. But if you build a new building, you could end up adding 878 CO2 equivalent when you replace the building. So, it is never a prudent design to immediately demolish a particular building. We must always first and foremost consider reuse and retrofit of existing building. Now, the second strategy which we can use is, if you have decided to tamper with the existing building, try to reduce the amount of new built environment. So, if you see this graph, by proper planning and design, what can be done? So, this is carbon dioxide reduction potential. If you don't build anything, then you can reduce 100% CO2. So, if you build less, that is, you maximize the use of existing buildings and its asset and optimize those assets for operation and management to reduce the extent of new construction required, then you can reduce up to 80% carbon dioxide from getting emitted into the atmosphere. If you can build smart, clever, that is, you design the use of low carbon materials. You use only low carbon materials and you streamline the delivery process, then you can minimize resource consumption and CO2 reduction can be reduced by, and CO2 emission can be reduced by 50%. But if you build efficiently by embracing new construction techniques and eliminate the waste, then the CO2 reduction potential will be by 20% only. So, if you decide you need to demolish and rebuild, then try to reduce the amount of area or replacing the building material by very small number. So, if we look at carbon emissions by building types and building elements, we can see that for large and heavy buildings, the foundation and structure occupies or consumes largest amount or largest percentage of CO2 emission, and the same is with small and light buildings. Whereas if you renovate, this whole foundation and structure percentage becomes 0. Now, and if you see external cladding, then in large heavy buildings, small light buildings, there is considerable amount of carbon dioxide emissions. Whereas when you renovate, that aspect also becomes 0%. And if you look at interior finishes, that occupies or that also emits certain amount of carbon dioxide. And when you renovate, that is only the major portion of CO2 emissions. And then building systems and other items also are part of carbon dioxide emissions, and all of this can eventually be reduced if you renovate existing buildings by reducing the new built form. The third strategy is, you need to reduce below grade construction, which is actually basement, because see, architects can encourage reduction or even elimination of basement parking, and because of that a large amount of concrete can be saved, because concrete is a carbon intensive material. Also, carbon that is released from the soil during excavation, that can also be saved. So, both of these can lead to large embodied carbon impacts. So, it is found that basement and retaining walls, they discharge a lot of high embodied carbon, and therefore we need to ensure that we reduce the basement area, because we consume concrete plus emissions from the soil. Both of these can lead to very high carbon dioxide emissions. You see, if you look at any building, you will find when there is more CO2 emission in particularly in any particular component, you will find that most of the time it will have something to do with concrete, steel and glass. For example, foundation, or floors and roofs, window and external door. All of these are made of energy intensive material, and therefore we can try and see how we can reduce CO2 emissions by completely eliminating below grade construction. The fourth strategy you can follow is to use appropriate, simple and advanced passive strategies based on the climate of that place. So, what are simple passive strategies? Now, here I have classified passive strategies or passive techniques into two types. One is advanced, one is simple. So, what is simple passive techniques? Simple passive strategies are strategies that do not require any specific contraption to capture, store and release any kind of heat in the cold climate and chillness in the warm climate. So, they operate purely on natural principles of conduction, convection, radiation. So, these strategies do not require any specific contraption or gadget. Whereas, advanced passive techniques, they work where you need certain contraptions like collector, absorber, storage, distribution and sometimes even control system of heat or chillness. So, you need a device to collect heat, absorb heat, store the heat, distribute the heat, control the distribution of heat. As an example, I am saying. Further, advanced passive strategies can be segregated or they can be classified as passive cooling and passive heating system. Examples of passive cooling system is, say, natural night ventilation, earth to air heat exchanger, evaporative cooling, passive downdraft evaporative cooling, radiant cooling, green roof, wind tower, double skin facade, double roof, etc. And passive heating strategies include trombe wall, solarium, water wall, phase change material, earth air exchanger, thermal siphoning, earth air tunnels. And simple passive techniques, they use concepts like appropriate layout, proper spacing between buildings, enhancing air movement within the building and around the building, using correct size of openings, positioning the openings properly, giving adequate and proper sunshades, using correct walling material with appropriate U value, using the appropriate roof material with correct U value, ensuring that rain protection is given to the building, ensuring that there is proper storm water drain or collection. So these are all the strategies, and based on where you want to design, you must choose the correct technique so that you can reduce the operational energy of the building. I have I am taking another course which deals exclusively on this, which is called as bioclimatic architecture, future proofing with simple and advanced passive strategies. In that course I am taking this all of this in detail, and therefore I am not going to repeat it in this course. Then the fifth strategy you can do or you can follow is choose the correct building materials and building systems. So what do you mean by that? You see in this graph what is the embodied energy of various building material, and here you can see that aluminum is the material which has the highest carbon dioxide emissions, and this is followed by fiberglass, brass, and a set of metals like brass, lead, zinc. Of course, plastic, steel, copper, they fall next. But we also have very low embodied building materials such as brick, straw, stone, timber, plastic, etc. And then you have the medium ones, which is insulation, cement, glass, ceramics. But if you actually see, you should not see embodied energy only per unit. You should also consider how much of that material is used in a building. For example, if you see aluminum, we are not going to use 100 tons of aluminum in a building. But you see, there may be some other material which will be used in a larger quantity whose embodied energy may be less, but then that contributes maximum to the building's carbon footprint. So you should use appropriate building materials, and by that what I mean is, if we look at the embodied carbon of concrete, and if we see what happens when we use concrete in its conventional manner, then you see that the embodied energy is quite high. But in that concrete, if you are going to mix 30% as GGBS, then what happens is you are able to reduce this no reduce the amount of carbon in the concrete. So this material classification according to their global warming potential can be high carbon materials, low carbon materials, and climate negative materials also. So there are several alternatives in the market, and we can also be very innovative in how we combine these building materials. Even low embodied carbon finishes, no, they represent a small part of the total, but they can have a positive impact when you start adding up the rest of the improvement measures and help to further reduce emissions. Now, considering exposed concrete for floors and ceilings is also a very effective way to reduce finishes and therefore reduce embodied carbon. So, here I have given some list of high carbon materials, like if you use ground granulated slag from blast slag, ground granulated blast slag in cement, you can reduce considerable amount of embodied energy. If you increase your GGBS by 50%, then you can further reduce the CO2 emission as compared to conventional concrete. So, if we look at examples of high carbon intense material, we can see that triple insulated glazing, wood aluminum window frame, PVC window frame, wood window frame, waterproof membrane polyethylene and steel. These are all examples of high carbon materials. Whereas, if you look at low carbon materials which can have a positive impact on the environment, these are mineral plaster, solid wood or softwood, ceramic tiles, bamboo cladding, bamboo flooring, solid wood, hardwood for finishing, gypsum plaster board, CLT, GLT, and so on. Concrete deep foundations, clay plaster, these are all climate positive. For example, if you have to have a cladding insulation, then you can use recycled polystyrene, or which is like foam glass, which has minimum 60% recycled and new glass with mixed carbon. Then you can also have innovative building materials also, but I am not getting too much into the various building materials and their actual characteristics and properties, because again for that I am no offering a new course or a different course which is called building materials as a cornerstone to sustainability. In that I am handling and dealing every material separately. But coming back to this, we can have a climate negative material such as hardwood, GLB, CLB, hemp fiber, reed mat, straw, all of these can be climate negative. So, in today's class, we saw only the first few ways of reducing embodied energy in building through building material usage, and we will continue the other ways in which we can reduce embodied carbon in the buildings. Until then, thank you.